Hello everyone. Welcome to day 2 at RISC. We have a fantastic lineup of talks and discussions today, and we hope you'll enjoy them as much as you did yesterday. We will begin the day with a keynote talk by Dr. Nagarajan Natarajan, Principal Researcher at MSR India. His current interests are inspired by big challenges we face today as we increasingly deploy large black box large language models in real systems like copilots. Dr. Nagarajan received his PhD from UT Austin. Today he will explain how one can robustly customize large language models spanning prompt engineering, fine-tuning, as well as post-training alignment.
Yeah. Good morning, everyone. Am I audible at the back? Okay. Okay, so yeah, thanks for the intro. So today I'll talk about some of the machine learning work that's happening at MSR India, and in particular some of the things that I've been pursuing in the last few years since the ChatGPT moment that happened. So before I go into some of the details of the problem and the work that I'm doing, I wanted to give you a sense of AI work at MSR India. And of course, MSR India is a big research lab. It focuses on various things like theory, systems, work at the intersection of AI and society, and so on and so forth. But because my talk is going to be primarily a machine learning talk, I want to sort of showcase the research pillars that is around AI at MSR India. And one of the important research thrusts that we have is frontier retrieval models. So today you hear a lot about reasoning models, right? So you hear a lot about models that are being released by companies as well as in the open source domain. But what people are not focusing on is this problem of retrieval, which is how do you accurately and efficiently retrieve relevant documents from a very large corpus consisting of enterprise data or even the web data for a given query. So here is an example. So Microsoft has copilots like this. If you have Windows operating system, you may have this Copilot app in Microsoft. So typically users, especially enterprise users who are like parts of organizations and institutions and so on, they can ask these kinds of queries. For example, what are the important projects featured in the recent tech summit, right? So maybe I have the context of what the recent tech summit is, and I just want to get a sense of what were the important projects featured, right? And typically these Copilot applications, of course, they use large language models behind to understand this question, to prepare a response for you and so on. But for these responses to make sense, in fact, these large language models don't know the enterprise context. They don't know what tech summit is. They don't know what are the important projects that I have, right? Because these models are trained on the web data. So they don't have a context of what enterprise data is. Which means that the Copilot has to talk to a retrieval engine that interacts with documents like emails, chats, and so on and so forth to be able to ground the responses that this Copilot is going to give, right? So even though these models are exceedingly good at preparing responses, they know a lot of world knowledge, they still don't have a knowledge about the projects that I work on, right? Which is very personal to me. So which means that retrieval plays a very important role for the success of copilots. So that's why we are focusing, retrieval is an important focus area at Microsoft Research. And one of the biggest questions that we are going for is, just like how OpenAI and other companies are building these very large models that do reasoning, we ask the very similar questions for retrieval. Can we build a trillion parameter model that is primarily meant for retrieval? That is, the goal of the model, it uses all its parameters to be able to successfully and accurately retrieve the documents that the Copilot needs for the LLM to do its job accurately. The second big research area around AI at MSR India is reasoning. The term that's often thrown about these days a lot. Even though we don't fully understand what reasoning is, we only have a sense of what reasoning is. We don't formally define reasoning, but I'm going to stick to the term just because it is familiar and it's in the vernacular today. So the problem is, how do you formalize, how do you evaluate, and how do you improve the ability of language models to reason, plan, and act? And we work at various settings, right? So one setting is interaction with problems. These are problems which are completely closed. Math, logic, and coding, where if the problem is presented to you, just in the context, in the memory of the LLM, you can try to solve the problem entirely without relying on any external knowledge, without relying on any external sources, and so on. So we can completely solve the problem. using, let's say, this sort of chain of thought type of reasoning. So that's one setting. The second setting is where you have to go outside of LLM to solve the problem. Imagine settings like software engineering agents, right? So it's not sufficient for the LLM to generate piece of code that you want. You also want to make sure that the code actually runs. It first compiles, right? Which means you have to interact with the compiler to ensure that the code that is output by the LLM is good. And furthermore, not only does it compile, you have to ensure that you can write some test cases and show that the code is actually doing what it's intended to do. So you have to go outside of LLM's boundary to be able to solve the task. So which means that, so this falls under this umbrella of interaction with environment. So not only the context of the LLM, but also outside the context of the LLM, you have to interact with tools to be able to solve the problem. And finally, you take the environment all the way to humans, right? So imagine you are using copilots to solve tasks such as preparing for meetings, right? Or preparing for your exams next week. And then you can say, or writing executive reports for projects. So which means that this has to be sort of a human in the loop kind of a task. The LLM says that, hey, these are the projects I found. Do you think I can write about these things? And the human says, yes, this makes sense. Can you just go ahead and prepare a report for me? And then the LLM goes away for a few minutes or even hours and then comes back with a very detailed report like how a human would write, right? So we are trying to solve these office tasks that would take humans, experts, assistants, office assistants, hours to do. So can we solve these kinds of tasks with a little bit of nudge and interaction with the humans who are actually wanting to accomplish this task efficiently? So these are the sort of different settings where we are looking at. And in the rest of my talk, I'll focus on these kinds of problems where that involves coding and software engineering. So the next roughly 30 minutes or so, I'll sort of start with the motivation of the LLM landscape and what are some of the real world application challenges that are thrown at us constantly, despite the advances of these large language models. And the second part of the talk will focus on the title of the talk, which is robust customization of LLMs. What is the problem we are looking at? Why are we studying this problem? And what are some of the solution approaches that we have developed? And in general, the community has been thinking about. Right? I'll focus on two settings, black box and white box settings. I'll get into the details later on. And finally, I'll end the talk with some open research questions that you can think about as you step into the next phase of your career, and some of the exciting opportunities in MSR India as well as broadly in India. Yeah. So as you know, LLMs are getting increasingly better at hard benchmarks. You see news articles written every day. When was the last time where you see news articles about machine learning models, right? So we are living through such an era where normal magazines pick up on machine learning models and sort of make news about how good they are, right? So this is one of the, I also want to flash such a slide that says that these models are actually becoming very good. So these are some of the state-of-the-art models, GPT-4 o 01, which is the reasoning model from OpenAI, and the Claude Sonnet, and then Google's Gemini, right? And these are some of the very hard benchmarks. At least these used to be very hard, like MMLU, which is language understanding, and math is math problems, academic textbook problems. And then GPQA is a recent benchmark. I think it's called Google Proof QA. That is, you cannot Google these questions and get an answer, which means LLMs have to actually work through the problem to solve. And these are grad level science questions, so you can actually read the question. It's pretty challenging, even for an expert in this domain. They will have to use a scratch paper, or they will have to go to textbooks to refer to understand some of these questions before they can, maybe they also need to do a little bit of math to come up with an answer, right? And of course, they will have an explanation as to why they think the answer is correct. And as you can see, on this GPQA benchmarks, and experts, like people who do PhDs in this field, they get about 65% on this data set. And you can see the models are catching up. This dark pink, I think, is GPQA. And you can see the models are already catching up human ability on these benchmarks. And of course, people keep coming up with complex benchmarks. So the most recent complex benchmark is called Humanity's Last Exam. So as you can see, there is a finality to the title of the data set, right? So we want to create the last exam, which is very difficult. And not surprisingly, these models are struggling. Even the latest model is actually less than, around only about 10% accuracy. And to give you a sense of how difficult this benchmark is, so this benchmark is classified into different topics like classics, ecology, chemistry, physics, mathematics, computer science, and so on and so forth. And they seek experts from various colleges. These are professors, students, doing PhDs, and they submit questions. And that's how this benchmark was created, about 3,000 problems across domains. And you can see, right, it's a fairly complex question. It is also multimodal, right? There's an image, and an inscription, Roman inscription image, and the question says, hey, can you translate it? And it also says, and it wants a translation of this palm marine script, and it also asks it also gives a transliteration of the text in case it's not able to read, because I think many of these cases you can evaluate on models that don't understand images as well, which means that this forms as a hint to those models that cannot process the images. And there's another question in ecology. You can read through the question. It's very difficult, and even though the final answer is answered with a number. So these benchmarks give a flavor of natural sciences, math, and so on. And even in the coding world, these models are catching up. So one of the most popular benchmarks today in the coding world is what is called SWE bench, which is software engineering benchmark. And this benchmark is this benchmark is roughly about slightly more than a year old. And this benchmark started with this question, which is given an issue description. An issue is something like, when you go to GitHub, people typically submit issues, right? Like something fails. Hey, I ran this code, something broke, right? Typically, you write some description, or you say, hey, this is the piece of code I ran and it failed. So it has such an issue description that someone submitted, and then the full code base. It could be as big as a Django code base or a Ruby on Rails code base. So these are hundreds of thousands of lines of code. Right? And then given these two as input, the goal is to produce a patch, which is basically what you will submit to solve an issue that fixes the issue. Right? And usually there are some golden test cases that are hidden to the model that they will run and see if the patch that the model produced solve the issue. Typically the patch is applied to some function somewhere, or maybe two functions in two files in the entire code base. So the challenge is to first find which files you have to fix, and then also find the right place where you have to fix, and also try to validate that fix. So it's a very challenging problem. And in fact, when it started out, when the dataset was published a year ago, the state-of-the-art model then was GPT-4, and it was, even if you told the model that this is the file you have to fix among all these files, the model would only get about 5% accuracy on this benchmark, which means it could not solve 95% of the data set. But look at where the models stand today. In just a year, right? Sonnet is already breaching 60, O3 Mini is breaching 60, and many of these models. And 4.5 is at the latest model from OpenAI is close to 40%, right? This is also a very impressive achievement. So it's all good, right? So these models are actually catching up, and we are also throwing harder and harder benchmarks. So what stops us from using these models day in and day out in all the applications that we are building, right? The problem is that there are several challenges that arise in the real world applications that in particular these models find challenging in many scenarios, right? So here is one scenario that I'll use throughout the talk, which is a reasoning scenario in Bing search. So the task is to infer if two search queries share identical intent or not. So imagine you're a user typing a query into the Bing search engine, say things like restaurants in NYC. Let's say you're in NYC and you search for restaurants in NYC, and then some other user might be searching for, let's say, restaurants in Manhattan or restaurants in the Big Apple, right? So one of the important problems there is to target ads against these queries, or let's say target even relevant responses to these queries, right? So beyond these systems you need to know which queries are identical, which queries are not identical, to be able to give very targeted ads, because they will usually have a training set of some certain number of queries, and the model needs to be able to understand which query is identical to which query, so that it can take the ad for that particular query and show the user. Now this actually turns out to be a very hard problem, because these models have world knowledge. Of course they know NYC is same as New York City. Of course they also know that Manhattan is inside New York City. They may also know that New York is the state of New York City. But in many cases we don't go literally, right? The world knowledge cannot be applied literally. Sometimes I would say if I search for new restaurants in New York, I would treat that query to be same as restaurants in NYC, because oftentimes I don't spell out city. Even though city is in my mind, I'll always say restaurants in New York just because I know that the model will assume that NY means NYC. Right? So there are lots of connotations in the way we interpret the system, we query the system, which means that the world knowledge of these models are not going to help at these are kinds of precision tasks. These are surgical precision tasks, right? I need to know which queries are identical. So the world knowledge is not going to help. What is going to help? Experts are going to help. Experts can create labels. Experts know that, hey, this query and this query are identical because I've been in this field for several years. I know that this is how these queries, I have domain knowledge to say that these queries are identical, right? But scaling these, ideally what I should do is that I should get these experts to create these labels for many queries and then be able to improve these models. But it's a challenging problem because how many labels can you get, right? Even if you crowdsource, right? And I really cannot crowdsource because I really need experts in this particular domain who has been in this ads field for a long time to be able to generate these labels, which means that it is a challenge to create quality labels to be able to improve the performance of models like GPT-4. And secondly, GPT-4 is also by itself cannot solve the problem because it depends on cultural and geographical biases, right? The same question can, the same two queries can have identical connotation in the US, but not in UK. For example, cricket, right? It could mean something in UK, which is very likely the game of cricket, whereas in USA it may not mean the game of cricket. It's very likely to mean the insect cricket. So these biases creep in so that you cannot just label two pairs as yes or no. It also depends on what geography these questions are asked, who is asking these questions. So there's a lot of things that go behind these scenes that it's very difficult for models like GPT-4 to just blindly apply the world knowledge it has to be able to infer the answers. So if you do simple few shot, like if you extract some labels, like if you extract some labels from humans and then put those labels in what is called the few shot prompting. If you attended Sunita's talk yesterday, she talked about this in context learning, right? So you can put those examples in the prompt of GPT-4 as saying that, hey, these two pairs, they're identical. These two pairs, they're not identical. These two pairs, so you can just create these list of examples and then ask the GPT-4, hey, now for this new two pairs of questions, the new pair of questions, can you tell me if they're identical or not? So you can write this prompt, but this prompt is not accurate. This strategy is not accurate simply because it's very difficult for the model to generalize, because the questions that you have picked to put in the prompt, the examples you have picked to put in the prompt often will have some bias. They'll be from some market, some geography, some type of questions and so on, and GPT-4 can easily latch on to those biases, and by latching on to those biases, it's not going to generalize. So that's why this problem is very challenging. So despite these models getting better, there are these tasks that keep coming on everyday life that somehow surprise these models, right? So another task that I'll talk about is what is called software engineering in copilots, in code copilots. If you use VS Code and GitHub and so on, today they have copilots everywhere. And so code editing, so editing code to satisfy what is called non-functional requirements. Typically, if you look at the benchmarks, what do they ask, right? Hey, produce a code. Here is a test data. If the code runs on the test data, you're good. If the code fails on the test data, you're bad, right? So this is what is called a functional requirement. You just test for functional. Does this code sort the array? You can check if the code sorted the array, you're done, right? But in real world, when I deploy these models in the copilots, the developers look for various other kinds of requirements, not just functional requirements. Right? They look for what is called non-functional requirements. Things like, hey, this is a code that sorts the array. Can you make this in place? Can you improve the complexity of the algorithm? Can you make this more memory efficient? Can you make this streaming instead of batching? So these are the kinds of questions that people ask, and these are refactoring kind of questions, right? They're not functional. They're beyond functional. You look for a certain non-functional aspect of the code. And how do you even test that non-functional aspect of the code? Right? First, you have to show the equivalence of the code. The code that you generated also sorts the array, but it sorts it more efficiently, right? So it's a very complex problem to even specify. So therefore, the models also struggle. And in fact, we put together a benchmark that consists of these kinds of examples. Like, so here is this is a real code from an Android repository that what the developer is trying to do is trying to optimize bandwidth usage, because this piece of code is going to run on your app. So it helps to optimize bandwidth by, let's say, not downloading a file if it already exists, right? So these kinds of optimizations people do all the time, and this and the kind of benchmarks that people evaluate, they don't capture these kinds of scenarios. So we went ahead and created such a benchmark. This is another example where, yes.
This is like a vocabulary question. I'm just curious, why are you calling this as a deployment challenge?
This is a deployment challenge because one of the places where we want to deploy LLMs in Microsoft and in general is places like GitHub, where people create these kinds of issues. And a lot of issues that people create are failures, not just because, let's say, a feature. Very few of the things are things like, hey, add a feature, but many of these cases are refactoring type of things. Hey, I want to rewrite this code.
So you just mean the benchmarks are missing some real life scenarios.
The benchmarks are missing some real life scenarios, and the benchmarks, even if the models do very well on those benchmarks, it doesn't mean that when you apply them on real world scenarios where you face problems like refactoring and security. This is another example, security. You want to do this try catch, you have to raise the right exception and so on. So these are important things that people care about in deployments. And these are not functional in the sense that I cannot write a test case to show that, hey, you've done it correctly. I mean, of course you have to pass whatever test cases this passes, but you have to do something more than that, right? So that more than that is what real world deployments require, and these benchmarks don't capture that. And we did go ahead and create such a benchmark called No Fun Eval, which is a pun on non-functional evaluation. And we showed that leading models, in fact, struggle to do well on these kinds of benchmarks. And there are several blind spots of these large language models. In fact, we could very clearly see that accuracy is significantly worse on these kinds of tasks than on functional tasks. Like all the bar charts that I showed you where the accuracies are breaching the human level accuracies, they are true for certain type of tasks, but for these kinds of tasks that we're interested in, and in fact we should, as a community, should be interested in, their accuracy is significantly worse. And even O1 is actually not much better than GPT-4, but in general you see that O1 is almost always better than GPT-4 in all the evaluations. So okay, so I'm moving on to, so now that we sort of understand some of the challenges and some of the deployments, issues and things like that, I'll talk about some of the work we've done in sort of making correctional sort of actions towards these, right? So what do I mean by customizing LLMs, right? So typically, what do you do, right? So you have an LLM checkpoint either via OpenAI. OpenAI gives you an API, or Anthropic gives you an API. So that's one way of accessing the models. In some cases, you might have the model itself if you're using a Llama model, which means you can just download the model and start using it. So, but however you typically start with some checkpoint of the model, and then you have to take this. You have to go from here to some deployment, right? The model is actually sitting inside an application like Copilot, right? So in the black box setting, which is probably the most common setting because we are often behind an API like OpenAI, the best thing you can do to customize these LLMs is prompt tuning, right? So which is, I don't have access to the model weights, but I can at least try to improve the prompt so that it does better on the task that I care about, right? So if you recall the first scenario I talked about, which is the Bing search scenario, where the goal is to identify if two search queries are identical of internet or not. This is a very good example of this setting where OpenAI's models are sitting behind some wall, and the only thing I can do is to improve the prompt that I can write, right? And I also told you that the in-context learning, standard in-context learning does not work. So the question we want to ask is, can we go from a simple one-line task description, which is, hey, identify if the two queries are identical or not, just that one-line English description of the task, to a detailed human-like prompt, how a human would write. In fact, I'll show you how a human writes this prompt. So in fact, there are engineers in the company, not just in our company, every company, who write these kinds of prompts which are very elaborate. These are like pages and pages of prompts. They write detailed things, and it helps to write this level of detail, right? So things like, hey, you're an expert in Bing search domain, your task is to convey if the two given search queries asked by real users in the Bing search share identical or not, and blah, 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 and then you will have paragraphs talking about corner cases, what gotchas, what is important, what is not important, right? Things like, hey, you have to focus on brand specificity. That is, you should identify two queries as identical only if they talk about the same brands, even if they slightly differ in the brands. One is talking about iPhone 15, one is talking about iPhone 16, then I should not consider them as the same query. So you have to impart all these things by prompt, and humans actually they spend weeks writing these kinds of prompts and testing it against data to see if it gives them slightly better accuracies and so on and so forth, right? It's a very laborious process. So one of the things that we did recently is sort of mimic what humans do using LLMs. So we tried to answer this question, you just using LLMs and using these kind of gradient descent kind of algorithms, but on text data, can we go from one-line task description to a nice elaborate essay-like prompt with detailed sections and examples and things like that, right? I don't know if you can read this, but typically these prompt optimization methods work very much like SGD, right? How do you do SGD typically? You have a training data, you have a model, you first apply the model on the training data, compute the loss, and then wherever so you basically try to go in the direction that minimizes the loss, which means that you typically form a batch of examples, compute the gradient, and then take a step in the negative step, and then you iterate. So this is how you do it. You can surprisingly do a very similar thing on text, right? So that is what you can do is that you take an example, let's say the question, this is a different data set, it says, tell if the following is a hate speech or not. This is a hate speech classification data set. And then you give those examples to an LLM, and the LLM says, hey, LLM will make some correct predictions, some wrong predictions. And then you take the wrong predictions and then you give it to a quote-unquote expert LLM, which could be another instance of LLM like GPT-4. And you can ask, hey, these are the examples that it made a mistake on this batch. Can you give me a corrective edit to the prompt so that these mistakes go away? So the LLM says, hey, you know what, you did this, maybe you should try to add this. Maybe you should try to add this. So LLM gives, for each example, it gives you suggestions, and then you ask this LLM to take the initial prompt and the suggestions and apply it. This is like the actual parameter update kind of step, right? So this is the gradient step, this is the update step. It's very mimicking the real continuous world things, but on the discrete world. And it's surprising that these kinds of algorithms actually work, and people are actually trying to build theory. In fact, I saw a paper called TextGrad from Stanford that does exactly this, but it builds a whole theory, just like how in TensorFlow and PyTorch you have this backpropagation for neural networks. Now Stanford had built a very similar pipeline for text, just dealing with text, and guess where it appeared? This paper, it appeared in Nature. So these things are being considered as fundamental science. These kinds of machine learning algorithms today are being considered fundamental science. So we do a very similar thing, but we make this one observation that maybe it helps to batch these wrong examples to identify why they are going wrong. That is, we try to cluster them. We cluster like failures. If certain examples failed in the same mode, if they failed for the same reason, we try to cluster them. And we ask the model, this is like something like mini batching, right? If you're in SGD, you do this mini batching. And then we try to get feedback for each of the mini batches, hoping that for the examples that are similar within the batch, the feedback is also likely to be similar. So you get similar feedback. Hey, for example, this one you could say that, hey, you should add a section on racial discrimination, right? Because that's an important part of hate speech. And then maybe these examples will say, hey, you should add a section on general articles on violence, right? So it can come up with very, very precise feedback for each of these like examples, and then the expert LLM can then give very, very precise edits to your prompt, and then you can finally aggregate them and apply the edits. And we find that these kinds of, again, going further ahead to SGD and applying these sort of mini batching and so on, further improves the accuracy of these prompts, and we're able to actually get prompts that are very human-like.
So why are we not passing correct predictions in the prompt to the expert LLM so that you can effectively contrast between?
So I'm not showing this. We do also. In fact, we do have some correct examples to ground. So that's a good point here. So I also include citations and papers in the slides. So later on, you can just go and look at the paper if you want details. I'll also talk about the white box setting where you have access to the full LLM. Right? So far, we were in the setting where you only have AP access to the model. But now, let's say we are in the setting where you have full access to the LLM because these are, let's say, open source LLMs, which means you can change the weights of the model, and let's say also have the compute to do this fine tuning. And if you look at the white box steps, right? So I also wanted to just sort of have an instructive slide that tells you about how typically people go about tuning these models, right? So, for example, if you're in OpenAI, this is what you would do. So this is how they, for example, created GPT-4. So they start with some web data, and then they pre-train the LLM. By pre-training, this again sentence completion loss, next token prediction, right? In almost in all the cases, the loss is almost always the same, which is next token prediction. And then once you have some base model, then for the application or for other reasons, you may want to fine-tune the model. That is, which means you will collect more data, more sort of supervised data, more principled demonstrations, that the kind of data that users will want to use the system. They'll create such data and then further fine-tune these weights, arrive at a different checkpoint, and then in 2022, this thing happened. What I call the ChatGPT moment happened, right? They realized that you can not stop here, but you can go further and generate responses from the model, because I'm going to deploy this model, which means that I want to understand what kind of responses come out of this model. And then you can generate sample multiple responses from the model and give it to an expert, a human expert. Hey, which of these responses do you think are the better ones? Give me a ranking of these responses. They take this feedback and try to further improve this model in a contrastive way. Hey, this response is better than this response for this question. This response is better than this response for this question. They realize that by doing so, they can actually deploy these models to the end users. Things like in ChatGPT, where users ask questions and the model can in turn try to be accurate, try to be polite, try to be helpful. So so this training made ChatGPT possible, and this pipeline, the first ChatGPT that came out in maybe end of 2022 was by such a pipeline. And of course, sitting in Microsoft, if I want to build applications, I have to take this checkpoint and see if it's good for my application, or should I do something more so that I can make this even better for my application. So in this talk, I'll talk about this part, where some of the efforts that we are doing in this part of the pipeline, which is the fine-tuning part of the pipeline. And I'll focus on that scenario, the second scenario, which is software engineering copilots. So the problem is this: I want to customize code LLMs for code editing. Yeah. So code editing is a very particular scenario among all the things that you can do with code. Code generation, code summarization, code understanding, and so on and so forth, which these models are pretty good at. But code editing is a very specific scenario where the full code is given to me and some instruction is given to me saying that, hey, can you make these changes, right? Or can you make this better? Or can you make sure that this error goes away, right? So you have some expression of intent, and the code is given to you, and the goal of the model is to output pretty much the same code, but with the edits that you want, right? So which means that there has to be preservation of functional correctness, functional equivalence. At the same time, the model also has to achieve the task that you want to do. That's why it's a slightly different downstream scenario than what these models are actually built for. And of course, you can imagine applications in VS Code, Visual Studio, and other places. And this is a one-slide summary of what we have done in the fine-tuning stage that I showed you. So we are able to take many of these open source models that are out there, which is state-of-the-art, like Qwen Coder 2.5, which is one of the state-of-the-art models for coding. Models like DeepSeek and so on, and we are able to improve them. We know that these models struggle in the benchmark that I initially briefly talked about, right? This no fun eval, which is evaluating on the non-functional aspects of code. So these models do struggle, continue to struggle on those benchmarks, and but we are able to consistently improve every model in the family by fine-tuning using our algorithm and our data, and able to produce better models that are better in very precise sense. They are better in the code editing tasks that we want the model to do, and they're also better in the original sense. That is, they also do the tasks that they originally did well, they continue to do them well. So if you attended Sunita's talk yesterday, she mentioned two kinds of things when you talk about robust adaptation. One is you want the model to do well on the tasks that you're helping the model to do better, and by doing so, you don't want to overfit, right? You also want to make sure that the model originally, if it was doing better on 10 other tasks well, you want the model to continue to do better on 10 other tasks, only that you also want it to improve on the 11th task, right? So you can think of code editing as the 11th task. So we show that not only is it doing very well on the 11th task, but it is also doing as good or sometimes even better on the original 10 tasks, which I think is the success of this work. I don't know if I have, can I take 5 minutes to complete the details and then I'll be done. So then maybe I have the details of how we got to this results in the slides. Maybe you can go through this. I'll spend some time talking about, or if during the questions we can come back. I'll spend some time talking about some of the open questions that are in this space, right? And then maybe, if time permits, I'll give you some sense of the method itself. So many open questions are there. So one is, can we improve the quality of edits with test time compute? Because you're seeing these models like over and R1 style, if we allow more time for these models at test time, like you say that, hey, this is the piece of code I want to edit, this is how I want the edit to be run, but take 5 minutes if you want, take 10 minutes if you want, come back with a very good edit for me, right? So how do you train these models to capitalize on the test time? The fact that you have more compute available at test time, can the models capitalize on it to come up with better and better quality edits? This is a very important question. So this question is not just with respect to edits, but also you can ask this question with respect to any reasoning task that you want to do. This is one of the sort of hot areas in research today, which is this test time compute. And the second one is, can we do similar robust adaptation for general models beyond code? You take any reasoning model out there, and you have some scenario in mind. Let's say you want to solve some problems with respect to, let's say you have some domain in math or some domain in chemistry that you find that the model is struggling, you want the model to improve. But can I do a similar adaptation such that it improves on the domain that you are improving, at the same time it preserves all other goodness, which in generally it has. So how do you do that? And the algorithm that we have is general, so I didn't have the time to talk about the algorithm, but maybe you can look at it. I have given references as well. And finally, an important question from a verification point of view is that how do I know that the edits that the model is generating are good, right? Can I verify the edits? I use the word verify in a very formal sense, right? Like if you attended the keynote talk yesterday. So can I leverage formal methods to make these edits, and can the models ascertain some guarantees about the edits they are making? So that's a very important research direction from from intellectual curiosity point of view, but also from a very impact point of view, because users will always be happy if you just don't show the code, but you also give a certificate that, hey, this code is actually correct. And of course, you can, if you want to work on these problems, there are many ways you can work. Like Professor Varsha said, like you can, now you're at a point where you want to think about the next phase, and you can work on these kinds of problems, whether you do masters or PhD, or we also have a program called Research Fellows where we take fresh undergrads and prepare them for a career in research. And you can think of this program as roughly the first 2 years of a good PhD program. And in fact, a lot of the results that I showed is working with people like you who have come from IIT Bombay and worked with us. And we have some great students who've worked on several of these problems, and they're all the lead authors on all the papers that I write. So I'm very happy in working with these people. And so I'm hoping that these kinds of seminars and conferences encourage you also to take these paths. And RF Research Fellowship at MSR India is just one way to achieve to your destination, but there are many other programs in the country. You should apply to all those programs. And if PhD is what you want to do, then you make sure that your resume is strong enough so that you land in the program that you want. To summarize, so the real-world LLM deployments throw new and hard challenges, and benchmarking and the leaderboard numbers that we often see can only help to some extent. They're not fully reflective of the ability of these LLMs or the inability of these LLMs. And robust adaptation of language models is an exciting research area, and it's critical to the success of these deployments in real-world applications like copilots. And finally, it's a very exciting time to be doing AI research. Of course, it's also a scary time because you see lots of uncertainties, new breakthroughs every so often, but so be it. Thank you.
Questions and clarifications?
Hello. Hi, Dr. Narajan. So I'm Himanshu. So in the first slide, you have mentioned about frontier retrieval model set. So on 18 March, Microsoft released a fantastic research on something called KBLAM, knowledge-based augmented language models, that particularly claims that there's an end of RAG and in-context learning. And that's fantastic approach where they are integrating the knowledge sources directly into the attention layer, which they call rectangular attention mechanism.
Yeah.
So, like, what's your view on that? Like, is this end of retrieval or RAG, and how it's gonna be looking like in the next couple of years?
So RAG, right now RAG seems indispensable because a lot of this data is sitting in some private repositories, private code bases, emails, and so on and so forth. So it's unclear how much you can improve the models by integrating this data at the heart of the models, like while training and so on, because there are a lot of concerns like privacy and so on and so forth, which interferes with some of the things that you really want to do. So today RAG seems to be the sort of cleanest and safest way to do these things. But of course, I mean, as researchers, we want to try new architectures that support these kinds of ideas. But right now, it feels more like a research idea. But I don't know if it actually pans out. Yeah.
Like I was suggesting, please raise your hand in advance, the mic can go to you for optimize the mic time.
Hello, sir. Small thing. Usually, an anatomy of a prompt usually consists of goal, return format, warnings, and content dump. Now, even like take a model like Copilot or Gemini. Usually, these models tend to hallucinate. Even writing it in this format, you said people write prompts for like weeks, right? So, how do you prevent that hallucination actually?
So the reason people spend weeks to do this is to exactly avoid hallucinations, right? They elicit certain rationales, certain reasoning. So they put all these things in the prompt so that they nudge the model to do what it wants to do as best as it can, right? And of course, it is a model. It is subject to failures. So the only thing we can do is try to improve these models and catch as many mistakes as we can in the prompting stage. And if you want to further improve it, then you really need access to the model itself, right? So you need guardrails in the model. You need to be able to change the weights of the model. So in the black box setting, you can only do so much. By prompt tuning, you can only do so much.
Yeah. Thank you.
So, in the improvement that happened from 5% to 60%, what really changed in that 1 year span? Is it like the model was exposed to more code data, or some architectures changed?
This is I did not talk about it. So we have two ingredients that we attribute to the success. One is we create synthetic data. We have a very sort of rigorous pipeline that generates data that from the get-go has these properties, has these refactoring properties, and so on and so forth. That's one part of the story. The second part of the story is that we have a new algorithm that improves on algorithms like SFT, LoRa, standard algorithms that invariably end up overfitting because there is a lot of discrepancy. If you look at models like Qwen and DeepSeek, they are trained on, let's say, 20 trillion tokens. And the synthetic data that we are able to generate for code editing tasks is in the order of billions. Even if we scale, we cannot scale more than, let's say, a few billions, right? So this is several orders of magnitude different, right? So this is where all the machine learning, bias variance, overfitting, all these kick in. So we have an algorithm that tries to alleviate this to some extent, so what our algorithm is a variant of SFT, but it has some nice properties. And so the synthetic data as well as this algorithm together is able to do this.
Also, in non-functional tasks, what is the evaluation metric? Is it like conventional text metrics like Blue, or?
So we have an upgraded version of Blue for code diffs on code diffs. And second, in some of the tasks, we actually invoke static analysis tools. So we run a CodeQL and ask if the fix does not have the issue. So we have various metrics.
My questions are very basic, so hopefully. So I had, one thing is from yesterday I have been waiting to ask, when you all mean robustness, what's the metric?
So robustness, in most of these, at least in ML setting, robustness is usually, it can mean multiple things, but most of the robustness that you heard today and yesterday's Sunita's talk is what is called out of distribution robustness. That is, you're training these models using some samples from some setting that I want. In this case, let's say code editing. I create some synthetic data, which I think is representative of what my eventual goal is. But my benchmarks can look very different than the data that I'm mimicking, right?
So when you do say accuracy, you know that the benchmark is in your distribution. And when you say robustness, you are throwing some,
exactly.
like,
it
knowingly.
means that you're training on either a very small subset of data, which means you will incur the sampling bias and so on.
Okay.
Or your data, I have no idea what these test benchmarks are, but I know that because it's focusing on certain type of tasks, let me mimic those benchmarks and hope that if I train the model on this, I will be able to do better on that. That is the kind of robustness that we talk.
So one thing, overall, again, very basic question about all of the accuracy and SOTA things that you were showing. This 70-80% and all of that, sometimes it doesn't, the benchmarks and the ways to rate LLMs don't captures the ridiculous things they fail on.
Yeah.
Okay, so is there a way to quantify that? Like, and because humans, that's such a big divergence from humans, that when a human is trained and skilled to do something, they are simply never going to fail on some really silly, like we see this in code a lot.
Yeah.
We have many examples where we are just stunned at the output of the LLM, that how could it fail on this? So, has there been any way to quantify that?
Yeah, so people, so I did not go into these details. In many of these cases, we dissect these numbers. So for example, one of the ways we could dissect these numbers is, if I take the test data and split it into, let's say, very small files and very large files, right? So how is the accuracy similar? Ideally, I would expect the model to succeed on easy tasks and fail more on hard tasks. And if your performance matches this thing, then you're actually moving in the right direction. In many cases, what you find is that your accuracy is, let's say your accuracy is 50%, you are 50% accurate on easy tasks, you are 50% accurate on hard tasks. That's actually not a good setting, right? What we find is that you are, let's say, 60% accurate on easy tasks and let's say 40% accurate on hard tasks.
Thank you, sir, for this interesting talk. Our next keynote talk is from Dr. Priyanka Naik. Priyanka is a research scientist at IBM India Research Lab and is a part of Gen AI platform team. Priyanka's research has explored cloud deployment, networking, and observability of microservices, such as network functions, and extending the same for multi-cloud deployments. She has received her PhD from IIT Bombay, India. She is a co-author to a cloud networking book and has also recently been appointed as an ACM eminent speaker and looks forward to connecting with institutes to collaborate on tutorials and talks. Today, she'll demystify systems research, showing how it drives great technologies and products, and share insights on getting started in this field and the exciting career paths it offers.
Hello everyone, I'm audible till then? Yeah, so good morning everyone. We are going to switch gears a bit now in this talk about understanding how to do or what it means to do system research, right? So understanding where systems are in place today, let's go back to something that every one of us knows. So who all watched our ICC World Championship trophy match on Hotstar or Geo Hotstar like a month back? Right? And did you see that on the right-hand side corner of the screen, they were showing how many people were simultaneously watching this match with you? And did you just get on the number of what is scale at which they were handling the traffic or handling your viewership, and in such a way that there was no drops in any of your viewership. There was no buffering happening for any of you guys, right? So it was the same experience for me, and then I tried to read how did they actually go about and build such a system that would support such a huge traffic in place, right? So in that sense, we know they came up and built a very scalable system designed to support such a huge traffic. But at the end, it basically was a web application that was supporting these such a huge traffic, right? So web application is something that a lot of us kind of keep on building day in and day out sometimes in our projects as well, right? So what do you use or what do you mean by a simple design of a web application? There will be a client sending requests to your front end, there will be a backend service, and that will be talking to your database or a data store which will be having or storing the data, right? So this is kind of the system that you guys kind of build, right? So now I want this talk to be more interactive than me just talking. So if I wanted to make this simple system scalable, what would be your approach, right? What would you have done to make this system scalable, right? I want answers from you guys.
Redundancy in the backend.
Yes, okay, redundancy backend, right? I want answers from the students as well.
Breaking the backend into services.
Right?
For scaling.
Yes, and? Okay, yeah, sorry for the, yes. So you, as we said, we had to add redundancy to scale these systems, so you add more replicas to each of these services, right? And once you add more replicas, you need something to distribute your traffic equally or with some logic to these backend services. You need something called as a load balancer in front of these services, right? This is a simple system designed to scale your application. And what these guys also had was a cache or a CDN kind of sitting towards the client side so that they could cache the requests that were coming in and could handle it closer to the client itself, right? So this was kind of the basic architecture that systems like Hotstars, which actually handled such a huge traffic, could also build upon, right? And obviously, when you build on such a large scale, they had to support a lot of infrastructure to do that. They almost had around 400 nodes to be supporting such a huge traffic of our requests going to them. And that's where they required something called as an orchestrator or something to scale this system well, right? So that's where they used Kubernetes as their orchestrator, which ran applications in terms of pods, which ran application inside the pods on these Kubernetes environments, right? So this was kind of the basic architecture of Hotstars scalable design. Right? But what they saw was, once there was traffic coming in, they monitored the traffic going in, and they saw there was a lot of uneven traffic going in to these applications. They measured the traffic going in, and they thought this is not good because some nodes are getting huge traffic, some nodes are not getting good traffic. We should see how we can even out the traffic that's going to these applications. And that's where they thought we'll have to scale evenly, and that's where they thought it would not be making sense to just scale more nodes to Kubernetes in one Kubernetes cluster or one Kubernetes environment itself, but scale it across multiple clusters or multiple Kubernetes clusters, so that once they have more nodes, more Kubernetes environments, they could evenly distribute traffic across the nodes and the Kubernetes environments itself. And they brought down the traffic distribution to not be just haphazard as in the left side, but a more even out, that is not 10 Gbps traffic going to one node, but 2 Gbps traffic going to all the nodes or all your cluster environments, right? So once we scale the microservices, as we talked in the last slide, then we scale the infrastructure itself to support the huge traffic, right? There were some other nitty-gritties that they did and scaled down how they handled the IP addresses so that even distribution happens, how they created the private network so that there was security across how the requests were going to individual nodes as well, right? So there were a lot of internal details, but at the high level, the design was this simple. And that was a base of something that we'd use day in and day out, like any OTT platform or that we have been streaming or using as of now, right? Now, that's where you know that you need to have a system engineer or a system researcher in place, because without them, these systems wouldn't have been built or been sustainable in such a huge environment or huge traffic or huge population that's using OTT platforms or any web app or your phone apps nowadays, right? So with that, just one insight, and this was something that got published in a Uber paper. So I spoke about a Hotstar example, but the same thing applies to a lot of our apps as well. So Uber also said that this is kind of the map of the microservices that they run, right? So you can see the amount of microservices that they have deployed over their entire infrastructure to support our traffic, right? So you can see the scale at which these applications run, and that's where we as researchers can contribute and make these systems run better, right? Right, so taking a step back, as we saw a graph there where we saw the traffic not going well, and then they scaled that infrastructure to make the traffic go on evenly. How did they do that? Was through efficient monitoring. So what do we mean by monitoring is measuring your system, if it's running well or not, measuring its resource if it's running well or not, right? So for that, there are a lot of solutions in the market today which do help you do efficient monitoring, right? So there is something called as Prometheus, which runs on your Kubernetes environment, lets you measure metrics at various levels. I'll have a question for you guys on this later, but they'll measure metrics very well and just print out on your dashboards what's going well or what's going not well per metric, and you can zoom it out, zoom in out at various levels. Similarly, there is something called as Instana, which helps measure your logs or your traces that way. That is, trace in the sense when you write an app, you want to see if there are a microservice chain, if the microservice requests are going well in this microservice chain or not. So you can use these traces to understand if the requests are going well or not, right? So this is one kind of observability solution that can help you do these tracing well. The third solution is LogDNA, which is the third kind of observability that you will have in your system, is to understand if the logs are being collected. That is, in your simple cases, you put print statements if, okay, it's going into this function or not, is kind of a log that you're actually adding in your system, right? So if you're these are the logs that you understand if your system is running well or not, or just to print out or help you debug whenever there is an issue happening. Right? So there are these solutions in market today being deployed on your Kubernetes environment. But what happens is, once you scale across not just one cluster, across cluster, you want to collate metrics from across these environments, it becomes very difficult to manage and analyze all these metrics, all these data across these clusters, right? And the cost of these storage and maintaining of these metrics or observability data also becomes huge, right? So we call it an observability tax because it's a huge tax on anyone maintaining these infrastructures. Right, so we have a solution in place to help minimize these costs, and not to just minimize it naively, but doing it a bit intelligently. That is, analyzing that what metrics are important and what metrics can help any analytic downstream tasks that run on your system, so that you don't have a standard frequency, right? The solutions that I've just mentioned in the last slide have a standard frequency for all these metrics. That is, every metric gets sent at 30 seconds. But that's not what analytics functions need, because all metrics have a different importance. So you need to be able to have a tunable knob that can work at a per metric granularity as well, and that's where our system came in. We sat with your metric generator or metric producer, that is here the metric collector, and it could actually it could modify or do the transformations at per metric granularity before it being sent into the public cloud or the global cloud or the central cloud where the analytics run, right? So we did that at the closer to the metric collector to reduce the overheads of how much traffic gets sent for the observability itself across these clouds as well, right? We also open source this code, and it's available. You can check out the repo, you can fork it, open issues, and try this out as well, right? So with this, I want to conclude on this a part of the talk that observe smartly with managing less so that it's done efficiently, right? With this, because I talked about open source, yes.
Can you give an example of what are these transformations?
Yeah, so just there can be multiple transformations like filter some metrics at like only 5 metrics of last 10 seconds just send, or just aggregate after a minute and send, or just adapt if there is a, I'll just highly motivate you guys to open source whatever work or whatever project that you guys are working on. Right? So we said we monitored something. So I want to ask you a question. I said resources are being monitored. So what are the resources that we monitor? Any answers for that? Yes. Yes. Right? So you measure resources like CPU, memory, storage, right? And there are a lot of things that you can do once you measure that. But now that we've been talking about LLMs for a long time, what are these guys? What these pictures make you think about, right? Yes. Yes, so these are kind of Gen AI or LLM models that are being used widely now. But now that we spoke about resources, what is the main resource that backs these models? Sorry? VRAM? Okay, any other answers? Yes. Yes, the GPU is kind of the core resource that helps enable running these models at such large scales or running such large models. Right? So I think Natarajan showed about this pipeline. There was a data preparation step. This is kind of the typical pipeline for any LLM workload, but it ends on what is called as deployment. But there are things that can be done at the application layer, which Natarajan spoke about, but there are things that go below that, for deployment as well, right? When you run a training model, it cannot run on a single GPU. You have to run on multiple GPUs. How will you distribute or how will you send it across multiple GPUs is a question that a deployment engineer or someone who works on the lower layers of your stack for running your LLM models require. Right? So there are a lot of open challenges in terms of not how the model is running, but how the model is running on your system as well, right? So there are things, system aspects to it. We spoke about resources like memory, the compute like CPU or GPU, how they are best optimized to run your application is very important for running these models efficiently, right? So these are kind of very open challenges that are a lot of research work has been going on to run these well. So one thing that we've been coming upon in our yesterday's talk as well is DeepSeek. Right? So we thought there were models in place already, and DeepSeek came in and like revolutionized, oh, we could do a lot of things, and we are much better than other models. But in terms of what, right? So they said they were better in terms of how they were using their compute, or they could do their computations in much lesser resources. And there is a good paper on DeepSeek which talks about what kind of system optimizations they put in place to let them do that, right? So I'll talk about two of them in today's talk. One is around parallelism, how they efficiently used parallelism to improve their model performances, and how they improved the networking itself to improve the performance. Right? So before going in depth, just a high-level picture of how your GPUs work today. If you have an NVIDIA GPU, you be using CUDA as your primitive to talk to your GPUs. And internally, what they have is what is called a streaming multiprocessor, which is kind of the smallest programmable unit. And internally, it has what is called as thread blocks, which are basically threads that are performing the same operation. That is, all threads are performing the same operation, that is called as a thread block. And thread blocks, 32 threads kind of form one warp which you can actually execute or give instructions to run on, right? And if it's assumed that all these threads in that warp will execute similar operations, and if there are some divergence, there is a hardware notification that it comes in that the one thread has got divergent and it's not working well, right? So the conclusion is there is the smallest unit, that is SMs, that you can program and run on, right? So and the second concept that I would like to highlight around is parallelism. I spoke about that. You cannot run your training model on just one GPU. You need multiple GPUs to run your training model. So you need to efficiently use these multiple GPU models, right? And how you can do that is using good parallelism techniques. So there are multiple ways you can do parallelization across these GPUs. So one way is you can split your data itself, the training data or your tuning data that you're getting, you can split it across multiple of these GPUs. That's one technique. Like these are working in tandem, right? These, like this is not that you just use one of the parallelization techniques. These techniques in combination make your LLM or your workload to run well, right? The second kind of parallelism is model parallelism, where you split what you call as the weights in your model itself, right? So each layer has a lot of weights that get computed. You can split them vertically so that they can be split across these multiple GPUs and they can compute their computation itself, and then you can merge them after the compute is done, right? So at a high level. The third is pipeline parallelism, where the architecture consists of multiple layers, right? You can split the layers itself across multiple of these GPUs, and you can let them run parallelly, and then you can merge them to get the output. So this kind of is a pipeline parallelism that happens. But in pipeline parallelism, there are issues that are kind of bubbles happening. That is, if you run you run a model, run one layer, you're waiting for the other layer. That should not happen. So there are ways in which, there are techniques in which these optimizations have been done, that the bubbles or the weight gap between these techniques, these layers is reduced, right? And that is done using efficient configurations on what batch sizes being shared, used for each of the layers, right? So these kind of techniques are used to efficiently use the GPUs in the, by parallelizing or splitting your data, splitting your model across multiple of these GPUs, right? So the third thing I spoke about is networking. That is, they optimize on networking because, as we said, we had to use multiple GPUs. There were optimizations done on how GPU to GPU.
Yes. Sir, one clarification. Yeah. What was the difference between pipeline parallel and model parallel?
Model parallel, the weight was split, and pipeline, the layers itself are split. It's horizontal versus vertical split. Yeah. So the third thing we spoke about is networking, how you can optimize the networking itself. There are a lot of techniques that NVIDIA had put in their GPUs to improve the communication. So one kind of communication is GPU to GPU communication. Another is there won't be a lot of GPUs in your node. You have to also communicate across nodes. So there has to be optimization on how these communication across nodes as well happen, right? So one is how the GPU and the NIC can communicate faster way. They can have a shared memory that can be used, where the GPU, once the compute is done, put the data in a shared memory that can be picked up from by the NIC and shared across the NIC as well, right? So this is one kind of technique that they've put in. There is things like peer-to-peer networks, that is two GPUs itself. There is a protocol in place to improve the communication across your GPUs as well, that has been done. And there are things like direct I/O kind of thing that we have been using traditionally in our computer networks to optimize our communications. You do a direct I/O kind of thing to communicate with the GPUs as well. Right, so there are things in place to optimize your network as well. So just coming back to DeepSeek, there were things that I spoke about, that did efficient parallelization, did efficient networking. That is, they co-communicated used the networking well. That is, if there was some GPU to GPU communication happening, they used that time itself to do a cross-node communication itself, and did a parallel, they proposed a dual pipe protocol or algorithm which helped them run their communications in parallel with their compute itself, right? So you don't waste time on these networking or these communications. Your compute is running in parallelly. So in that way, they optimized on the time or the wait time that these applications were seeing or these workloads were seeing, right? So these all challenges are at the lower layer of your stack, that is your system or your memory or your compute or your network, right? And obviously there are a lot of these optimizations that DeepSeek put in place, but they are not the end. There are a lot of optimizations that we can think of, that we can do or we can propose on our own to these to the lower layer of your stack as well. Right. So coming back to what we are working at IBM Research, so we see that GPUs are in place, are kind of readily available now, but they are being used a lot by your LLM applications, right? But they need to be efficiently used. across your applications. And now, as you said, you have your data center in your institutes as well, which you are kind of sharing across your individuals that way, right? So this needs efficient management of these GPUs that are being used in the infrastructure, and something like these platforms that have been there traditionally will be in place in your institute as well to use these GPUs efficiently, right? There are LSFs, LLM, there are multiple examples of it, Kubernetes being the most famous of this because it's being used for microservices or cloud environment as well, right? But these lack what our Gen AI workloads need, right? So they don't do efficient GPU sharing. What I mean by efficient GPU sharing is once you ask for a GPU, you get one GPU. Even if you're not using it 100%, it's kind of dedicated to you. And other user comes in and asks for a GPU. If it's not available, he or she won't be able to run their workload, right? So we need to efficiently share the GPU so that they can run in isolation on the GPU, and a lot of people can use that limited GPU resources that are available in your infrastructure, right? So how to the infrastructure manager or your platform engineer or your platform should manage how these sharing happens across multiple of users efficiently, right? The second thing is something that a lot of you might have also experienced if you're running LLM workloads, right? You run out of memory most of the time. You get out of memory issue a lot of time. So it's because memory is a major bottleneck of running these LLM workloads, and there are a lot of open problems that can be done or that can be worked upon as system researchers to efficiently manage how memory is being shared, how memory is being used, how memory can be isolated across the applications to run your workload well, right? So that you don't run out of memory when you run your application. And of course, it's the applications that are running, that is the LLM workloads, as we spoke about parallelization, they can be really well parallelized compared to what other applications or the traditional applications that we have been running till now, right? So we have to efficiently use these parallelization techniques, or the platform manager or your where you're running your application should be aware of how these parallelization techniques can be efficiently used to run your AI platform, AI workload that way, right? So with that, I'd like to conclude by how you can get started, right? I spoke about two things. One is doing your web application, building a scalable system. Second is how you actually can use, there are layers on the stack when you are running your LLM workload itself that require system research, system engineers to run them efficiently, without which the applications get stuck or get bottlenecked by your resources, right? So try running your workloads, try measuring your workloads that way. It's not just getting them running is enough. Understand, run the measurements and understand why are they getting stuck, what is the issue that they are facing, and think about scale that way, right? So one thing is, once you realize they are being stuck, what you do is add more resources. Adding more resources is one way to scale your system, but it's not the only way, right? There is a limit of how much you can scale. So you should look for problems on optimizing the existing resources itself, so that within your existing resources itself, how well you can run your application, right? So that's what kind of becomes a system research as well, because there are optimizations that can work not just for you, but a lot of other people that as well, they can leverage your system or your optimizations and better build their systems or run their applications, right? So what kind of optimizations you can look for? This is just a starter. You can look out for recent papers in system research. There are top conferences which talk about optimization that you can use, you can incorporate. In fact, most of the research labs or most of the companies today use these research papers as the base to pick up system optimizations that can be incorporated into your systems, and they really see good improvements because of that, right? So optimize, scale, measure your system, and that's how your research journey in systems will start. With that, a bit around our hiring. We are hiring in our systems research group, our platform research group at IBM Research India. Do get in touch with me if you are interested. We have research opportunities as well. We have summer internships, 3-month summer internships. In fact, and our applications go out in August and so around August and September. Do look out for my post on our internship programs. We also give out a list of research problems that we are kind of trying to work in the next summer. So if you are writing some of the research problem, get in touch with the mentor who has put out that problem, and you can connect with us and work on that problem as well. And because I'm a diversity lead at IBM Research, we have a yearly diversity connect for students as well around September. So follow me on LinkedIn for that as well. And we hope to see you at IBM Research just to get a feel of how research is done at our lab. With that, thank you for the talk.
Oh, hi. I have a question in the observability volume manager. So in your architecture, would certain microservice metric that is being observed and the fluctuations in those have a priority filter? Like if there's a microservice change and some certain metrics is actually affecting the chain downstream, but it's not an issue right now, but some metric that needs to be improved further as during consolidation of the whole metric. So is it being filtered directly at individual metric level, or how is it working?
So that is also a way in which we give the flexibility, right? So we talk about a metric level, we can go down to a metric level, but we can go down to a microservice level as well. And as you said, can be priorities given, right? If there is a microservice which is talking to say 5 microservices, so that going down can impact like 6 others that way, like including it. So if that is a metric, that is a microservice that going down, then we can improve the granularity for metric collection for that microservice itself. So we can go down to a metric level, but the metrics can be for a microservice level or a cloud level or an edge level as well, right? So that is the tunable knob that we provide.
Morning, ma'am. I have a very basic questions. Like suppose I am developing some systems, but I don't want any human intervention to look into the matrices or the logs. So what I want, I want integrate LLMs to it, so that I do not have any system developers who is debugging that. So it is kind of self-healing systems what I am looking for. So how you are going to integrate that into the servers so that they are going to recover their debugs itself by themselves?
Okay, so we can talk offline as well, but the architecture that you will follow is kind of a closed loop system where you will need some installations at per microservice level or pure Kubernetes level, which is collecting the metrics, sending it out to your analytics engine. The analytics engine will throw out that this is the issue happening. Then there would be some standard issues that are identified. Then you will say, okay, if the CPU is going out, just scale it vertically or add more CPUs or just add one more replica. So that kind of standard definitions are there that can be defined, and that can come down to remediating it in the actual system. It can be a closed loop that way.
My second question would be like how you are preventing the DOS attack that your going system have. Like maybe you have given the example of GeoHotstar. So there may be some.
Sorry, I didn't get.
You have given the example of GeoHotstar servers.
Right.
So there may be many DOS attacks that are going to happen on the servers. So how you are going to prevent that?
Yeah, so one thing I spoke about is you create private networks so that your traffic doesn't go in, or you have what is called as a DMZ zone which actually filters your packets or sees if there are a lot of packets coming in, just drops packets, sees if it's coming from the same IP address or not, drops at that. There are a lot of policies in place, IP policies or network policies is in place to drop such and prevent such DOS.
There can be some multiple IP addresses also, like.
Yes. So you identified range. They are called as bots, which can come up anywhere in system. So you kind of learn what kind of the bots are coming in, what kind of traffic they are kind of generating. That can be a similar kind of packet or payload that they are generating. These are just techniques in which you can identify these traffic.
Are you integrating the rate limiter there also? Like rate limiter number of requests?
Yes, that can happen at a lower layer. Like at the microservice level itself, you can have a rate limiter so that such a request cannot happen. That is at a higher layer of the stack. That is at the application layer, you can prevent that. Okay, only 100 HTML requests can be going into a microservice.
Okay,
that kind of rate limiting out.
Hello, ma'am.
Good morning, ma'am. My question is, what are the current challenges in the system research and how we can effectively address them? And the follow-up question is that what is the role of artificial intelligence and machine learning in system research in perspective of jobs?
Okay, that's yeah. We can talk offline as well if I think if we. Okay. Yeah. So I understand there is a lot of curiosity and a lot of tension that if you're not doing LLMs, you're not using LLMs, you won't have a job or you're not doing relevant work. That's not the case. I understand. The applications have been there for a lot of years. There have been microservices that were deployed on cloud. LLM is kind of a use case, or you can consider them as application. Lower layer, there are resources. At the end, there are resources that are they being hosted on. That is, they need some resources to run on, right? So it was CPUs that were critical for your microservices. Now it's GPUs that are critical for your applications. So you can look for lower layer of the stack to understand that, okay, is my GPU working well? How can I improve it? Is my communication across GPUs working well? How can I improve it? If I'm deploying it on a Kubernetes environment, what are the challenges? Because GPU is kind of a new resources for these environments, right? So they are not kind of adopted or having the flexible knobs that they had or they had improved on when they were running resources like CPU, using resources like CPU and memory. So are there optimizations I can do for that as well, right? So that kind of opens up some system research problems in this area. And going forward, there would be other applications that can come in. The story might change, but the underlying system research will be required or will keep running. Just the resources might change, or the way you're doing, what resource you're using might change. But the system research or the concepts that you have been using, the OS courses or the networking courses that you've been taking in your undergrad or postgrads would help you build these systems well. These won't go.
Thank you, ma'am.
Hello. You talk about logs. Logs are huge, and they also eat a lot of storage also.
Yes.
I want to ask how to in efficiently way we can analyze these logs and generate some alerts in real time. Means that's sometimes we face issue.
Yeah. So I didn't talk about it. That was work done by one of my colleagues where what they are doing is they are summarizing the logs itself, that is picking up metadata from the logs itself, and based on the metadata generating metrics that can be used to generate alerts that way, right? So there are work on that. I can talk offline on that in detail.
Okay, fine.
I have a question regarding the observability. A lot of applications, Kubernetes and all, they don't have the observability part of it. Some standalone solutions like provide the observability metrics. So observability is getting attention day by day. So are you thinking about that we should integrate the observability as an in the design itself, design of the systems?
Yes. I'll say it in I spoke about a very general observability, but whenever you write a simple application itself, right, the first thing that you see is the correctness, that is, it's serving your request well. The second you see is how much you can scale or how much resources it's consuming, right? You run a top or just see how much memory it's consuming, how much CPU it's consuming that way, right? So the observability actually we kind of use observability in a very raw form in any application or any system that we build, right? So I won't say observability is becoming hot. It has been there and will be required for any system or a basic microservice or a basic application you build as well. The way you do may change based on your deployment type, but your observability has to be happen, or some measurement, some performance analysis, some performance measurements or analysis that is required.
Thank you.
So this was sort of, I think, related to what Nagarajan had spoke earlier as well. So a lot of code optimization today, like refactoring or making it more efficient, can happen via LLMs also, right?
Yes.
So now the question is, there's still some part of performance optimization is also a little bit of like black magic. You have to look at the underlying hardware, what runs, what doesn't run.
Yes.
So how much of this, like what you're seeing in industry, can be automated via LLMs or something, and how much of performance optimization still needs human intervention, that some performance engineer, the one that you wanted to hug in the slides, right? So some performance engineer, human intelligence is needed for performance optimization. How much of that is the case, and how much is can be done by LLMs today? Do you have a sense for that?
Yeah, so as of what we are seeing, it's not there. We really need our human, first manual effort to understand what's happening wrong, because there are a lot of layers in the stacks which are still being in building, right? The compiles, the graphs are being rebuilt, the graphs have to be optimized. So that layer, there is no LLM being used as of now. But maybe in future, once these processes get streamlined, maybe we can incorporate some LLM techniques to improve that. But as of now, nothing is there in place to do that.
So just a quick question about the platforms that you are, and some examples of tools that you were mentioning.
Yes.
Have you had some experience with doing non-NVIDIA GPU work? Because we've been trying to probe some stuff with AMD, and seems a little more open for doing system engineering work with GPUs.
Right.
So is there any kind of a...
Yeah, we do. I can talk to you offline, but we have a IBM AI accelerator chip that's coming in this year. So we are working on the stack for it, and seeing what works or what not works, what layer, how the networking can be optimized for AI applications itself. So there is work in that we are doing parallelly along with what we are doing. And the platform that I spoke about, there is a FMS HF tuning. It's an open source repo that's built by IBM, which is done as a platform to let you run your tuning models efficiently. That is all the optimizations in place to run your tuning models efficiently.
Yeah, which is, of course, I'll look that up too.
Yeah.
I was just wondering about lower layers, in the sense that, there's a lot of plumbing in the memory management layers, the drivers, even the SM schedulers, and things, which is really opaque from the NVIDIA story point of view.
Okay.
And I think AMD drivers let little more access into all of that things. And one view of systems is, of course, to have the end-to-end plumbing, but at the lower layers, I was wondering if there's more experience, or if you have any other take on, which platforms should, for example, students be working with, because I think that also exposes a whole bunch of inner details of what's...
So we also, this is how you get access to, we generally work with NVIDIA GPUs till now, so we couldn't go into that layer of things to see if we can optimize that way. But I think as an academic institute, we can look out for opportunities where we can run at that layer, or see problems, open problems there.
Thanks.
So I have a question on my student's behalf. So he's working on MLSys, but he is not well. He's listening live stream, so he will hear your answer also. So he's been actually trying to, do this model parallelism versus data parallelism, measure the latencies. We are trying to do exactly what your last slide said, measure things, find the problems to solve. So, so he's saying you explained, data parallelism, model parallelism, talked about latencies, but not how you measure these latencies individually. So the layers are done in sequential order, data is being passed from one GPU to another, there are latencies which you are trying to maybe do some other work in, and so on. So I think he's asking you about the instrumentation tools and so on that you might have used.
Yeah, so some things like we were using NVIDIA GPUs, so there are something like NVIDIA SMI got us the utilization sense that way, right? And if your workload is something like a training or a tuning job, there are something called as a trainer controller, which splits out how much time it took for each stage or each epoch of your application. So in that sense, we collated that, and
so there are,
and NVIDIA SMI also splits out the memory that you're using for your application. So, and it can vary with time. So you can see plot a graph and see how much.
So you do get direct measurement. You're not like doing estimations or anything.
Yeah,
you are being
we
able to
have a
measure.
work which one of my colleagues is doing on estimating. So because these training and tuning jobs are long-running jobs, just estimating how much time will it take. So do you understand how much resources need to be allocated for this job? Is kind of a work that we are actually parallelly doing, and for that also the data that we are getting it is from prior running these, doing multiple runs of these data on various heterogeneous hardware and getting these numbers.
Thank you. We'll take it offline after this. Thank you.
Are there any more questions? Thank you, ma'am, for such a wonderful talk. We will now break for a quick tea on the first floor of new CSE building until 10:45 a.m. After that, as yesterday, a curated collection of talks has been arranged across various research areas and will be presented by students in parallel sessions. This will be on the first floor of the new CSE building. These are also part of the competition, so please do not forget to vote for every talk. Please refer to the program schedule for details of the talks and make sure to attend and also vote for the ones that interest you. The talks will be followed by lunch in the same area.
Attendance, tell them to stay outside for those who haven't registered.
Those who haven't yet signed the attendance, please wait outside.
And after the talks today, we also have three research demos by research labs. These are going to be interactive and you can move around and check things out. The three labs are the Trust Lab, which is on implementing the traditional security operations center in a resource efficient way. Bharat Jain, which is on building India's indigenous LLM, and Bodhi Tree in collaboration with Tower Research Capital. So make sure you attend these. Please make sure your travel reimbursement documents are prepared for